doubts for now? So the next chapter is the 3 address code. In the 3 address code, there are almost one operator on the right on the instruction and no built-up arithmetic expression which are permitted. So basically it is a equal to b plus c, right? We have plus, which is an operator. So thus a source program expression like x plus y into z might be translated into 3 address instruction, which looks below, right? So we can deal with only 3 address code when it comes to the compiler. Even though if it has multiple complex values, right? If you have a minus b, a minus b plus b c minus d, right? So every term here needs to be narrowed down with one operator, because that's how the compiler will be built. And compiler will be built based on this case something called as 3 address code. Looking into the cases here, with the example which we saw with the above, so a source language like x plus y into z might be translated into this case here. If you see, first, what is the term which we do according to the priority? Again, BODMAS, right? Multiplication comes into picture. X into z is what I do. This I call it as t1. Then x plus t, this I call it as t2. Simple. This is my translated version of 3 address instruction which you see here, where t1 and t2 are compiled generated names which you further use. So 3 address code is a linearized representation of DAG, in which explicit names corresponding to the interior nodes of the graph. For example, I have an expression a plus a star b minus c, which we already have seen before with the example of the DAG, which looks in this way. So first, what is that which we are doing? Come to the leaf node. B minus c is what I do first. So this is my task 1, which I say is as T1, right? So which I call it and name it as T1. After this, which is the second one which I do? I can do with this, or I can go do with this, right? Because this b minus c, anyhow it has been shared. So here, making this term is star, left child is a, and t1 becomes t2. On the other hand, this t1 star d will become the other case, right? So here, plus left child is a, plus right child is t2. Now, if I can group this complete term here, this is my task 3. So similarly, what is task 4? Task 4 is b minus c star d. So this complete thing will be my task number 4. This will be my T4. And the whole complete thing, T3 plus T4. T3 plus T4 will be my T5. Got it? So b minus c alone is T1. So T1 star a will be my T2, and a plus T2 will be my T3, and T1 into b is T4, and T3 plus T4 will be my T5. Got it? So do we have any doubts with this topic here? Anybody has any doubts how to work out with the 3 address format? Pretty simple. Okay, moving on. If you have any doubts, kindly let me know in the comment section. So address and instruction 3 address code is built from 2 concepts. One is address and the other one is instruction. An address can be one of the following. Address can be a name, or it can be a constant, or it can be a compiler generated information which is temporary, right? For example, we saw a plus t1 is equals to t2, or t2 is equals to a plus t1. A is what? A can be a constant or A can be a name. So two chances for a A. Here it can be 10 plus T1 also. So if it is 10 plus T1, then it becomes, the 10 is a constant. If it is A, then A is a name. So T1 again, it can be another temporary generated information. T1 is a temporary generated information. That's what it says. For convenience, we allow source program names to appear as address in 3 address code. In an implementation, a source name is replaced by pointer to its symbol table entry. Right? Similarly, a constant, it's a constant value which will not differ. Computer generated temporarily means that's what the T1, T2 and much more. It is useful especially in optimizing compilers to create and distinct name each time a temporary is needed. Distinct name, this is very important because I cannot have the same temporary name and it yields to me ambiguity. Symbolic labels will be used by instruction that alter the flow of control. A symbol label represents the index of 3 address instruction in the sequence of instruction. Actual indexes can be substituted for the labels either by making a separate pass or by back patching. Right? So the case here, let's see. A list of common 3 forms. One is the assignment instruction of the form x equal to y operator z, x equal to y operator z, where this operator is a binary arithmetic or logical operator and x, y, z are the addresses. Assignments of form x equal to operator y. This is, I have only one operator, right? If I don't have a left child for this operator, then it's a unary operator, right? So it's just a unary operator where operator is a unary operation. So the third thing is copy instructions of the form, that is x equal to y, where y value is assigned to the value to the x, right? The value y is assigned to value of x. The fourth thing is an unconditional jump with the case of an instruction. Example, label L with label L. So once I encounter this statement, go to this particular label. That means jump towards the label L. Next is conditional jump of the form. If x is a condition, if it is true, go to L label, and if it is false, go to this particular label. These instructions execute the instruction with label L next to x is true and false respectively. If this condition is true, go to one label, this is, and if it is false, go to this label. It can also be a conditional jump. The next case is conditional jump such as x relation operator y, go to L, which apply a relation operator less than, assigning checking for the condition whether both are equal, greater than equal to, etc., where x and y and its execution of instruction with label L next stands for the relational operator, which you already have seen with our compiler design chapter 1 lexical analysis, where we dealt with respect to the flow diagram, right, with the cases. Then the seventh one, it can be a procedure calls and returns are implemented using the following instructions. So parameter x for parameters, call p and y for the procedures and function call respectively. Basically its form looks in this way. The integer n indicating the number of actual parameters is called p. N is not redundant below because the calls can be nested. The next case is index copy instruction of the form. It can be index based instruction also. X is equals to y of I, where I is actually an index of array with the name of y, right? So that element will be assigned to x. Basically it's a memory location of y. The instruction x of 8 is equals to some value such the contents of the location I, x of I is. So I units beyond x to the value of y. Looking into the example here, address and pointer assignments of the form x equal to address of y and x equal to pointer of y and pointer x equal to y, right? So consider the statement, do I equal to I plus 1 while a of I is less than b. Two possible translations. What it can do is, so I plus 1 is t1, right? So I is equals to t1. The second case is I into 8 will be my t2 and t3 will be equal to the case. So here, assuming a value to be for I with the value, and that becomes my t2, and this will be my t2. A of t2 will be t3. So this complete term will be my t3. If it's a condition now, if t3 is less than this v, then go to some label. Go to some label in the sense we have some value which it needs to come here because the condition is true. That will be something called as a symbolic labels. So again, if in cases there are I1 is equals to I plus 1, it's incrementing. So again I have I as t1. So t2 has some value. I into 8 will be t2. So these are the address locations which will be pushed, and a of t2 anyhow it is t3, and t3 if it is less than the value v, then you go for some, go to label L. So what was the label here? L. What was the value which was given? 100. That's why go to 100. So this particular case of 3 address format is assigned with the value of each line with the address and working on it. So this is called as position numbers. So the translation in A uses a symbol label attached to the first instruction. The translation in B shows position for the instruction starting with the position 100. In both translations, the last instruction is the conditional jump to both translations. The last instruction, the multiple I into 8 is appropriate an array of element that takes each units of space. Here the 8 which you see here is just the space which each unit has been taken. So if you have any doubts, kindly let me know. Moving on with the concepts of quadruples here. Quadruples have 4 fields as 3 address format has 3. So a quadruples has 4 fields which we call operator, argument 1, argument 2 and its result. And the example goes in this way. Plus will be the operator, y will be argument 1, z will be argument 2 and x will be the result. The following are some exceptions to this rule. Instruction with unary operators like x equal to minus y or x equal to y do not use argument 2, of course. Note that for a copy statement like x equal to y, operator is equal to, while for most other operators the assignment operator is implemented. Operator like param use neither argument 2 nor the result. That's one case which you need to be considered. Conditional and unconditional jump put the target label into result. If you can look into the 100 was actually a number, the address where the value was pushed, right? So for the conditional and unconditional jump, the target value, the target label is the result itself. So looking into the quadruples here, how do we work out with the quadruples? First I have a equal to b star minus c plus b star minus c. So first is minus c is a unary operator, so make it as t1, right? So b star t1 is t2, then plus of this is okay, here again minus c, this is separate, right? So minus C is again unary. So this is my T3. T3 plus T2. So here minus C and minus C both are same. So the names with the case, right? So this will be my B. This is the minus C is T1. B into T1 is T2. Okay, then I go here with this term minus C. Anyhow, minus C is my value. Okay, so T1, this is T2, and this complete term here will be T3. This will be my T4, right? So B into the term will be T5. So A is equals to what? A is equals to T5. So you can see here. This is about the 3 address format. When it comes to the quadruples, we have 4 field, right? So the 4 field can be looked here in this way, where I say that let me clear off the case here. So here, looking for the first term, T1 equal to minus C. Here minus is the operator which we are working out. I have only one argument, which is C. So minus, I have only one argument, which is C, and what is the result? T1. Second case. So operator, argument 1, argument 2, result is T2. Then again minus, C is my only argument and T3 is the result. Operator, argument 1, argument 2, result is T4. So plus argument 1, argument 2, T5. So here it's a assignment operator. I have only one argument, which is T5, and the result is A. This is in the quadruples. The special operator minus is used to distinguish the unary operator. Fine. Next case is about the triplets. A triplets has only 3 fields, right? Operator, argument 1 and argument 2. Note that the result field in quadruples is where I work out with the result, but in the triplets I don't deal with the result straight away. So it is used in the primary for temporary names. Using triples, we refer to the result of the operation X, operator Y by its position rather than by an explicit temporary names. Example case here, A equal to B star minus C plus B star minus C. Looking into the case here, so A is equals to B star minus C plus B star minus C. Exactly, the diag looks perfect for this. And here, looking into the term, I have to go for minus C first. So minus C, so for minus C, minus, and the argument 1 is C. Next star, argument is D, and the right child is the complete minus C. Minus C is in location 0. So give the location of the argument here. Next one. So again minus C, right? So minus is operator and C is my argument. So the next case, star is the operator, B is the argument 1, and minus C is 2, right? So this location will be, the address will be copied there. So followed by, I have plus. This complete term is made as star, and this again this star. So this star is location 1 and this star is location, argument 2. So this is argument 2 and this star is argument 1. Ultimately we worked out with this. So equal to is the operator, left child or argument 1 is A, and the right child is the ultimate this plus. So this is at location 4. So the fourth location will be marked. Alright, so this is about the triplets. And the ternary operator like x of I equal to y requires two entries in the triplet structure. For example, we can put x and I in one triple and y in the next. A benefit of quadruples and triples can be seen in an optimizing compiler where instructions are often moved around when quadruples. If we move an instruction that computes a temporary t, then the instruction that use t require no change. Basically, we is giving the same case here. Alright then, we'll take up the topic of indirect triples in the next class. Thank you.